Before the cloud, building and running applications required buying hardware, hiring IT staff, and managing everything manually. It was expensive, slow, risky, and not very flexible. Today, cloud computing is a solution that changed everything. Instead of buying and managing servers, businesses can now rent computing resources on demand. With the cloud, there is no huge upfront cost. You pay only for what you use. Scaling is instant, so apps can handle traffic spike automatically. Hardware, networking, and backups are managed for you, letting you focus on building your application. Users anywhere in the world get fast access, and experimenting with new features is simple and cost-effective. Cloud computing frees businesses from the limitations of traditional IT. It makes launching, scaling, and managing applications faster, cheaper, and more reliable than ever before. Cloud computing has given rise to several major providers. Some of the most popular ones include Amazon Web Services, Microsoft Azure, Google Cloud Platform, IBM Cloud, and Alibaba Cloud. Among these, AWS, Azure, and GCP are the global leaders. These cloud providers offer a wide range of services to help businesses and developers build, scale, and manage applications efficiently. These services are generally grouped into 6 main layers: compute, storage, databases, networking, security, and monitoring. Compute provides the processing power to run applications and workloads. Storage allows you to save and manage files, data, and backups reliably. Databases provide structured and unstructured data management without worrying about manual setup. Networking ensures secure connections, traffic routing, and access control between resources. Security handles permissions, encryption, and compliance to protect data and systems. Monitoring tracks application performance, detects issues, and ensures reliability. Together, these services provide everything needed to run applications in the cloud without managing physical hardware, making operations faster, more reliable, and cost-effective. To utilize these services efficiently, organizations need professional cloud engineers. A cloud engineer is a professional who designs and manages cloud infrastructure. Most of the time, they are familiar with multiple cloud providers like the ones we mentioned and know how to leverage them to achieve business goals. There is also the DevOps engineer, whose main role is to automate deployments and build continuous integration pipelines. They do not manage infrastructure directly. Instead, they maintain secure pipelines that help software engineers deploy applications reliably on the cloud. Finally, because of the growing importance of cybersecurity, we now see the rise of cloud security engineers and DevSecOps engineers. DevSecOps engineers combine development, operations, and security. They build and maintain automated deployment pipelines while ensuring that security, access control, and compliance are integrated at every step. Essentially, DevSecOps engineers help software teams deploy applications safely and reliably on the cloud. A cloud security engineer, on the other hand, is a cloud engineer with additional responsibilities. They focus on access control, encryption, and compliance, ensuring that the organization's cloud environment is secure and follows best practices. In 2026, more and more applications are being deployed to the cloud, especially AI models. For example, GPT OpenAI model is deployed on Microsoft Azure. Companies today are demanding experienced cloud security engineers and DevSecOps engineers to ensure applications are secure, scalable, and reliable in the cloud. In this video, we are going to focus on both cloud and DevOps skills by deploying our NestJS API application into AWS cloud. This process will include DevSecOps tasks such as setting up CI/CD pipelines for automated deployment, integrating security checks into the build process, managing secrets and environment variables safely, automating testing, linting, and code quality, implementing access control and role-based permissions in deployment pipelines, monitoring pipelines for errors and vulnerabilities. We will also cover cloud security engineering tasks, including configuring network security with VPCs, firewalls, and security groups, managing identity and access using IAM roles and policies, encrypting data at rest and in transit, implementing logging and monitoring for infrastructure and applications. By the end of this video, you'll have hands-on experience in deploying a secure production-ready NestJS API application while applying both cloud and DevSecOps best practices. So let's start. Step 1. Source control. DevSecOps involves many steps. The very first one is source control. Source control, also called version control, is a system that helps teams track, manage, and protect changes to source code over time. It allows you to keep a history of every change made to the code. Roll back to previous versions if something breaks. There are two main types: centralized and distributed. Today, distributed version control is the one used by every developer. For example, Git. Git is a distributed version control system used to track changes in source code and help multiple people work on the same project safely and efficiently. Git alone solves versioning, but it does not handle collaboration, automation, and security. For example, if code only lives on developers' machines, team members cannot easily share it or work on the same project together. This is where Git platforms like GitHub or GitLab come in. They host Git repositories online, allowing teams to collaborate, track changes, and enforce rules. In this video, we will use GitHub as it is the most popular platform. So go to GitHub and log in or create a new account. Click on New Repository. Give your repository a name. I will name it NestJS DevOps. Add a description if you want. Choose public to access GitHub's free features. Then click Create Repository. By default, GitHub creates a repository with a main branch. After opening your project, the first thing we need to do is check whether it is initialized with Git. If you see the .git folder, you need to delete this folder so that you can connect your own GitHub repository. If your project is not connected to GitHub yet, open your terminal and initialize Git with git init. This command creates a local Git repository in your project. Once you do this, you will notice that Git automatically starts tracking some files and folders. The ones that are not tracked will appear in gray. You will also see a file called .gitignore. This file tells Git which files and folders it should ignore essentially. It is a way to prevent unnecessary or sensitive files from being tracked. Next, we need to stage our files for the first commit. To do that, run git add dot. This command tells Git to track all the changes in your project and prepare them for commit. Once staged, we can commit the changes with git commit-m first commit. This command records a snapshot of your project at this point in time with a message describing the command. Think of it as saving your progress in a game. Now that we have our local Git repository ready, it is time to link it to our online GitHub repository. To do this, copy the following command and run it in your terminal. Git remote add origin followed by GitHub repository URL. This command connects your local repository to the remote repository on GitHub, so changes can be pushed online. Next, we set the default branch name to main using git branch-m main. This command renames your current branch to main, which is the standard name for the primary branch in most GitHub repositories. Finally, push your changes online with git push-u origin main. This command uploads your commits from the local repository to GitHub and links your local main branch to the remote branch. Once all these commands run successfully, reload your GitHub repository, you'll see that your repository is now synced with your local project and everything is linked properly. Inside your project, you'll find a root folder and within it, an API folder that contains your NestJS application. Now we can start implementing our CI/CD pipeline. CI/CD stands for continuous integration and continuous delivery. Continuous integration, CI, means that every time you make changes to your code, those changes are automatically tested and validated. This helps catch errors early. Continuous delivery, CD, means that your code is automatically deployed to a staging or production environment after passing tests, so releases are faster and safer. To run a CI/CD pipeline, we need automation tools. Some popular options include GitHub Actions, built directly into GitHub, Jenkins, open source automation server, often used in AWS environments, GitLab CI/CD. In this tutorial, we will be using GitHub Actions as a default CI/CD automation tool. You can use other tools if you want, but keep in mind that the pipeline code syntax will be different for each tool. All workflows in GitHub Actions live inside a folder called .github. Inside this folder, we create another folder called Workflows. This is where we define our pipeline. Files in YAML format. You can create multiple workflow files, but in this example, we will keep just one file to manage both the CI and CD pipelines at the same time. Our pipeline will be responsible for building our NextJS API, running tests, deploying the API to AWS. What is YAML file? A YML or YAML file is a human readable format for structured data similar to JSON, but cleaner and easier to read. The basic building blocks are key value pairs, lists, and nested structures. In a workflow file, the first key we usually define is name. The name takes CI/CD NextJS to EC1, then EC2. On specifies the event or events that trigger the pipeline. There are many types of events such as push happens when you push code. Pull requests happens when someone opens or updates a pull request. Workflow dispatch happens when you trigger the workflow manually. Schedule happens automatically on a set schedule. You can check GitHub Actions documentation for more information. Here, in our pipeline, we want to trigger the pipeline when we push our code to GitHub. And we also want to trigger the pipeline manually for testing purposes. So, we will use the events workflow dispatch and push. In CI/CD, an event can have filter options. In our case, the push event will have the branches filter option, which specifies which branch will trigger this pipeline. This means that if you push code to another branch, like development, it will not trigger the pipeline. Next, we need to specify the name of the branch that should trigger the pipeline. In this case, it is the main branch. In a CI/CD pipeline, the on key specifies the event and jobs specifies the workers. A job is a set of steps that run together on a specific environment. This means we are going to specify many steps or tasks. The first step is to run the CI task. This task will run on Ubuntu latest. Ubuntu latest is a runner that works in a Linux environment. It's a virtual machine provided by CI/CD platforms. Here, we are not limited to Ubuntu. We can also use other runners like Windows latest or macOS latest, each used in a specific environment. But why Ubuntu and not Windows or macOS? Ubuntu is a Linux distribution, and most programming languages such as Node.js or Python package managers and Docker work smoothly on Linux. As DevOps engineers, Linux is a core fundamental skill. The cheat code to learn Linux is to install Linux on your machine and use it every day, or install a virtual machine on your Windows or macOS computer and use Linux. After setting the runner, we set the tasks themselves using the steps key. The first task is to check out the code, which is usually the first step. This allows us to copy or download our repository's code onto the runner so the job can work with it. We could do this ourselves with git clone, but there is a more productive solution using a pre-built GitHub action. A pre-built GitHub action is essentially a reusable task or a script that someone has already written, tested, and published. Instead of writing everything from scratch, you can just plug it into your workflow. These actions live on the GitHub Marketplace, where you can find any action you need for your project and use it. For example, we can search for the checkout action and see every detail about it. What it does, how to use it properly, the latest version available, who the author is, and all published versions. You can also publish your own action if it solves a real problem. Back to the code editor, we can continue with the next step. After gathering the repository code, we need to set up node.js. We will use another action called Actions Setup Node. Make sure to always check the latest version published by the author to stay updated. Here, we can just put the name of the action in the search bar. Then review all details and even check the open source project on GitHub. Next, we need to specify the node.js version that we are going to use with the with option. This option has another option called node-version, which takes the version number. To identify the node.js version, type in the terminal node version. If you use this version to build your project, use the same version to run your pipeline to avoid errors. Next task is to install dependencies. To install node dependencies for the project, we will use the run key, which takes the command npm ci. Why use npm ci instead of npm install? Because it cleans the node modules folder and installs exactly what's in package-log.json. Now we need to specify the directory where the node modules should be installed, because the package-log.json file is located in the API folder, not at the root of the project. Next step is to generate the Prisma client with npx prisma generate. This command is a Prisma CLI command. It reads your Prisma schema from prisma/schema.prisma file and generates the Prisma client, a type-safe database client your node.js code uses to interact with the database. Without this step, your code cannot access the database via Prisma because the client does not exist yet. This step ensures the client is generated fresh and matches the schema before tests or deployment. Next step is linting with the command npm run lint ci. Linting checks your code for syntax errors and coding standard violations. This command runs the lint script defined in your package.json. Before we continue, we need to set up our lint system with NestJS. Open the package.json and look at the scripts section. This script runs EXLint, which checks your TypeScript JavaScript code for errors in all TypeScript files inside source or apps or libs or test folders. It automatically fixes formatting issues with the fix option. The primary goal of the CI pipeline is not to solve errors, but to detect issues early in the development life cycle and then report and block deployment. This is the mindset behind DevSecOps. Detect errors upfront in every step, not later, to improve security. We'll create another script called linked CI for CI specifically. Here, we remove the fix option. Then run npm run lint and npm run lint CI. We also need to specify the working directory. Next step is to run tests using the command npm run tests. This is a big step where we set up tests in NextJS. By default, NestJS uses Jest for testing, a popular JavaScript testing framework used by NextJS, NestJS, ExpressJS, and more. You are about to learn how to set up Jest properly with NestJS. By default, NestJS provides a minimal setup, but this is not complete. If you try to run npm test, it will fail due to path issues. Test files generated by NextJS, like controller spec and service spec, need to import dependencies. For example, the payment service test file needs to import the payment service class. So first, install Jest packages for development only. By default, NestJS puts Jest configuration inside package.json. For now, we'll use the default config but make some changes. Replace the root directory option from src to / because we are using Prisma, which is located at the root of the project. Also, add a new option called module name mapper, which tells Jest how to resolve import paths. For example, when you see an import starting with src, redirect it to the real src folder. After that, we can run tests again. Path issues are resolved, but we might encounter dependency injection error. NestJS uses dependency injection, meaning controllers need their services injected automatically. For example, user's controller needs user's service. Open then the controller test file and add a providers array, each object representing a provider. Inside each provider, we use the provide option, which takes the class needed for the controller test. Here, we define the user's service. We also add another key called useValue, which takes an object of functions defined in the user's service. For now, we don't need to specify these functions. We can leave this object empty. And that's it for the user's controller text file. Now we can test it and check whether the user's controller test case fails or succeeds. Great, as you can see, the test case succeeded successfully. What we are going to do next is simply repeat the same process for all other test files. Of course, we are not going to dive deep into writing advanced test cases like API testing and so on. The main goal here is to set everything up properly and make sure pipeline runs successfully. Now let's continue with the other test files. Let's start with the off module. Here we have a controller test file. We'll do the same thing by adding the off service. But the off controller needs more than just the off service. It also requires the config service, the Prisma service, and the JWT service. So let's add all these classes. Next, we do the same for the off service test file. Great. Now the next file is the category controller test file. The category controller needs the category service. After that, we have the category service test file. Next, we move on to the other controller test file. And then the other service test file. After that, we have the payment test file. Next, the product controller test file. And now the product service test file. Finally, the user's controller test file. After all this setup, we can run npm text again. Great. Now we see that only one test is still failing. This is the main app controller test file. And that's it. We are done setting up the tests. Next, in the CI pipeline, we are going to audit dependencies using npm audit. npm audit scans dependencies for known security vulnerabilities and reports them. This is security scanning, not functional testing. Now, the first job, CI, is complete. The second job is CD, called deploy. A job can have a dependency. Here, deploy depends on CI. This means CI must complete successfully before deploy starts. If something goes wrong in CI, the deploy job will never start. The job runs on Ubuntu latest and requires some permissions. ID token allows the workflow to request an OIDC OpenID Connect token used for secure authentication to cloud providers. Since this job deploys our app to AWS, GitHub Actions needs access to our AWS account. The most effective way is using API keys. However, API keys are not completely safe. If your GitHub account gets hacked, attackers could access your AWS API keys. This is why we use OpenID Connect instead. OIDC is an identity protocol built on Auth 2.0. It lets one system prove who it is to another system using signed tokens instead of passwords. There are no API keys and no long-lived secrets. We'll see how it works later. For now, let's move on. This job also needs permission to read repository contents such as code, files, and commits. So the first step is to get the code and then configure AWS OIDC using the AWS Actions. You can check this action on the GitHub Marketplace to see what it does, how it works, and which options we need to provide the role to assume and the AWS region. The role to assume argument takes the AWS role, and we also specify the AWS region. For more information, you can check the OpenID Connect documentation where you will find everything needed to configure OIDC properly. The first step is to establish an OIDC trust relationship in AWS. Next, the GitHub Action requests this token as proof. Finally, AWS validates the claims in the token and provides a short-lived access token available only for the duration of the job. This is amazing because it solves the problem of long-lived secrets. The token is rotated automatically and it only works while the workflow is running. Once the workflow finishes, the token is no longer valid. At the moment, this is the best security approach to connect a cloud provider with GitHub Actions. This may differ if you are using other automation tools. Now that we understand the concept, let's start. The first thing to do is to create a GitHub Cloud role in AWS. If you are new to AWS, welcome. You can create an account and get access to AWS free tier. Follow the sign-up process. You will provide information such as your country, address, payment method, and phone number. All of this information is mandatory. If everything goes well, you will land on the AWS dashboard, which is the home page. Here you will see recently visited services. If this is your first time, you probably won't see anything yet. The next step is to set up security and identity. In AWS, the service that handles this is IAM, which stands for Identity and Access Management. Identity defines who you are. Access defines what you can do. Management controls permissions. You can search for IAM using the search bar or click it directly if you have used it before. Once inside IAM, we are going to create a user group. A user group is a collection of IAM users that share the same permissions. So first, we create a new user and then add that user to our group. Click then on Users, then Create User. Fill out the form. Enter a username. I will call it admin-user. Select custom passwords and set your own password. Then click Create User. Next, click Add User to Group and create a new group. Name it something like admin. Attach the administrator access policy to that group. This policy grants full access to all AWS services and resources in your account. Then click Create Group. Go to the next step. Optionally, add tags. And finally, click Create User. Great, the user is created. AWS provides a CSV file containing the account credentials. You can download it for backup. Now, go back to to the IAM dashboard and create an identity provider. An identity provider, or IDP, is an external system that AWS trusts to authenticate identities. Here, we will create one for GitHub. Provider type is OpenID Connect. Provider URL, write token actions.github-user-content.com. For the audience, this is sts.amazonaws.com. Tags are optional. Then click Add Provider. After creating the identity provider, the next step is to assign a role. Click Assign Role, then select Create a new role. Choose Web Identity. And fill in the identity information. Enter your GitHub username. Leave the rest as default. This allows the role to be used across repositories and branches. Now attach the required policies like Amazon EC2 Container Registry Power User, Amazon EC2 read-only access, Amazon SSM read-only access. These policies allow EC4 access, EC2 read access, and Systems Manager read access. Continue, give the role a name. For example, GitHub-actions-deploy-role. Add a description if you want. AWS generates a trust policy automatically. To avoid issues, make sure your GitHub username is lowercase. After that, finish the setup and create the role. Once the role is created, we need to store it as a GitHub secret. Go to Settings, Secrets and Variables, then Actions, then Secrets. Add a new repository secret. For the name, set the role name. For value, set the role A or N. Create another secret for the AWS region. You can get the region directory from the AWS console URL. Backend or CI/CD pipeline, we can now reference the role and region using GitHub secrets. At this point, we've completed the first major step, logging into AWS using OpenID Connect. Next step is to log in to AWS ECR. We need to authenticate Docker so we can push and pull images. This step uses AWS credentials from the runner, requests a temporary authentication token from ECR, logs Docker into ECR using that token. You'll notice a new secret called ECR repository. Let's create that. Go to Amazon ECR. ECR stands for Elastic Container Registry. It's a managed service that stores Docker images. Create a new repository. Set the repository name. Choose mutable image tags for development. Image tag mutability controls whether an existing tag can be overwritten. For development, use mutable tags. For production, immutable tags are recommended. You can also define immutable tag exclusions. Immutable tag exclusions like v**. For encryption, data in transit is encrypted with HTTPS. At rest is encrypted automatically with AES 256. ECR encrypts images by default using AES 256. No configuration is required. For advanced security, you can use a KMS key, which gives you control over key rotation and auditing. Create the repository. copy the repository URI and store it as a GitHub secret. Back to the CI/CD pipeline. Next step is to build the Docker image. We use Docker build with no cache option to force a fresh build. The ECR repository name, the latest tag, the working directory is API. Next, we push the image using Docker push. Before deploying, we test everything locally. Install Docker Desktop, which lets you build and run containers locally. After installation, start Docker. Create a Docker file at the project root. This file defines how the image is built, step by step. So here, we start by defining the Node.js version we want to use. In this case, it is Node.js 25.5, the same version we used to build the project, and the CI/CD pipeline. Next, we specify the Linux distribution we want to use. Here, we are using Alpine. Alpine is a very small and fast Linux distribution, commonly used to build lightweight containers. You can find more information about all the Linux distributions available for containers Docker Hub. If you search for a node and select the node image, you'll see all available Linux distributions and their versions. Finally, we give this stage a name, which is Builder. Next, let's continue. We set the working directory inside the Docker container to /app. All subsequent commands will run from this directory. Next, we copy package.json and package-log.json. Here, the asterisk symbol matches any file that starts with package. So both package.json and package.lock.json are copied from the local machine into the image. Then we also copied the Prisma folder from the local project into the image. After that, we install the production dependencies using npm install. Next, we copy everything from the local project into the container. Then we generate the Prisma client using npx prisma generate. And after that, we compile the application for production. Now we define another stage. This stage is for production. The first stage was used to build the application, and this second stage is used to run the application in production. We start by defining the working directory inside the container, again using the /app folder. Next, we execute a command inside the image using apk, which is the Alpine Linux package manager, similar to apt on Ubuntu. Here we install the package dump init. So why do we install dump init? This is a tiny init system for containers. It handles system signals correctly and prevents zombie processes. We also specify the no cache option. This prevents cached packages from being included in the image. The goal here is to keep the image smaller and cleaner. Next, we copy package.json and package-lock.json and the Prisma folder into the production image. Here, instead of rebuilding the project, we simply copy the compiled JavaScript output from the builder stage into the production image. We do the same for the Prisma client directory. And the prisma.config.txt file. Then we create a non-root user and group inside the container for security reasons. After that, we change the ownership of the app directory to the non-root Node.js user and group we just created. Next, we run the container as the non-root Node.js user, which improves security. We also document that the container listens on port 3000, which is best port used by Docker for networking. Then we set up a health check. This periodically checks the application's endpoint and marks the container as unhealthy if the check fails. The entry point handles system signals and properly cleans up child processes before running the app. Finally, we start the NestJS application when the container runs. This source main.js is the compiled entry point of the NestJS application. With this Docker file, we can now build and test our Docker image. Now, we are also going to create another file called docker-compose.yaml. So what does this file do exactly? Docker Compose allows you to define and run multiple containers using a single configuration file. Right now, we only need to build one container for our NestJS API. So things are fairly simple. But what if we also want to build another container for a PostgreSQL database? That's where things get more serious. Without Docker Compose, we would need to run each container manually, create Docker networks, link containers together, and this becomes very difficult when you have many containers running at the same time. Docker Compose solves this problem. Instead of doing everything manually, we just create one file and define everything inside it. For this specific project, we don't strictly need Docker Compose, but we are adding it in case you want to create more than one container later. Inside this file, the first thing to do is to define the file version. The version defines the format and features of the Docker Compose file. Different versions support different options, syntax, and levels of compatibility with the Docker engine. For example, version 3.8 tells Docker Compose which syntax, rules, and features this file uses. Next, we have the services section. The services section is where you define all the containers that make up your application. Each entry under services represents one container that Docker Compose will manage. Here we define our NestJS API service. We specify which image or build context to use. Context dot, which means the current project folder. Dockerfile, which specifies the Docker file to use. We also set a custom container name. This prevents Docker from assigning a random name. Next, we define the ports option. Ports map a port inside the container to a port on your host machine. The first port comes from the environment variable, port. This is the port you usually access in the browser, for example, localhost 3000. The second port, 3000, is the port inside the container. If this feels confusing, here is the key idea. Containers are isolated environments. Each container has its own network, namespace, and IP address. So your computer cannot access the container directly. To make a container accessible, we expose a port and map it to the host machine. This allows other services or your browser to communicate with the container. Next, we have the environment section. This section defines environment variables inside the container. These variables are read by your application at runtime. First, we define the name of the environment variable, and then we assign its value from the host machine. If you are confused about the difference between an image and a container, here it is. An image is a read-only blueprint of your application. It includes the operating system environment, the runtime like Node.js or Python, your application files and dependencies. That's what we call a Docker image. But an image's job is to run somewhere. When you run an image, it becomes a container. So it means a container is a running instance of an image. It has its own memory, file system, and processes. You can start, stop, or delete a container without affecting the image itself. That's it. Once this file is ready, we can start everything using docker-compose up. This command builds images if needed, starts all services defined under services section, streams logs to your terminal to stop and remove containers, networks. Next, we have the restart option. This tells Docker to automatically restart the container if it crashes, except when we stop it manually. Now, let's move on to the manual configuration. To build our image manually, we run docker build-t, followed by the ECR repository name, the tag, and the correct folder where the Docker file lives. This command builds an image from the Docker file and tags it with the name latest. Once the image is built, open Docker Desktop and go to the images section. There, you'll see the image name, the tag, the image ID, the size it takes on your machine, and a play icon to create a container. To run the image, we first need to specify a container name. Here, we will name it NestJS API-container. Next, we define the host port, which is 3001. By default, the container is already listening on port 3000. After that, we can set all the environment variables the container needs. In production, these variables are usually loaded from cloud secret managers. But for testing, we need to define them manually. Once this is done, we can run the container. As you can see, our NestJS API is working and the database is connected successfully. Great job! Now we can open the app in the browser using localhost followed by the host port, which is 3001. After confirming that everything works correctly, we are ready to deploy our application to EC2. To deploy the app, we will use the Apple Boy GitHub action. This action requires several parameters. The EC2 host, which comes from GitHub secrets, the EC2 username, and the EC2 private key. All of these values will be obtained from the AWS platform. So let's go step by step. First, what is EC2? EC2 stands for Elastic Compute Cloud, and it is one of the core services of AWS. EC2 allows you to rent virtual computers, also called servers, in the cloud. You can use them to run applications, websites, or anything that you would normally run on a physical server. Basically, if you want to run a website without buying a physical server, you can launch an EC2 instance with Linux like Apache and host your website there. Later, if your application grows and gets more traffic, you can easily scale by adding more EC2 instances. By using EC2, you are mastering one of the core cloud services, which is compute. Now, search for EC2 in AWS and go to the dashboard. Click on Launch Instance. The first thing you need to provide is the instance name. Just give your instance a meaningful name. Next, select an operating system. We want to run our app on Linux, so we need to choose our Linux distribution. There are many options available here, and you can even search for specific ones like Arch Linux. By default, AWS selects Amazon Linux. Amazon Linux is AWS's own Linux distribution, optimized for EC2. It's usually the best choice when creating an EC2 instance because it is free, lightweight, secure, and well integrated with AWS services. It also comes with the AWS CLI pre-installed, which saves you a lot of setup time. That said, if you prefer a different distribution like Ubuntu, that is totally fine. Next, we select the architecture and then the instance type. An instance type defines how powerful your virtual server is. It determines CPU, memory, network performance. By default, AWS selects T3 Micro, which has 2 virtual CPUs and 1 gigabyte of RAM. With this instance type, we can run Node.js and Nginx together, run Docker containers side by side, handle multiple HTTP requests. However, this instance is not suitable for heavy CPU workloads running continuously. So always choose the instance type based on your performance needs. Now let's move on. AWS gives you several ways to connect to an EC2 instance. One of the most common methods is using key pairs. Key pairs are simple. You create a key pair by giving it a name, selecting the key pair type, choosing the private key file format. Then click Create. AWS will download a private key file for you. You'll use this key later to connect to the server using SSH. Let's store this key inside the project folder. Here it is. Now, make sure to add this file name to your .gitignore because it is a private key and should never be committed to Git. Next, go back to AWS and configure the network settings. Here, I'm allowing SSH access to the EC2 instance. For development, you can allow access from anywhere to avoid connection issues. In production, you should restrict this to a specific IP address. I'm also allowing HTTP and HTTPX traffic from the internet. This controls who can access your web application. If you don't want your server to be publicly accessible, you should not enable these options. Next, we configure storage. This is the disk space for the EC2 instance. Here, I'm choosing 8 gigabytes of storage. GP3 is like an SSD for cloud computing, and 3000 IOPX defines how fast the disk can read and write data. After that, we can leave the remaining settings as default and click Launch Instance. Once the instance is created, select it to view the details. Here, you'll see the public IP address, which is used to access your application from the internet. If you open it now and see not found, that is expected. We'll fix it later. You'll also see the public DNS, which is simply a domain name that points to the public IP address. Now we need to store these values in GitHub secrets. First, create a secret repository EC2 host, which is the DNS. Then EC2 user. For Amazon Linux, the default username is EC2-user. And finally, EC2 key. Paste the private key content here. Great. When you launch an EC2 instance, AWS allows you to provide user data. User data is a script that runs automatically when the instance starts for the first time. So here, I write scripts. I can start adding the scripts I want to execute. The first script downloads the Docker image from ECR to EC2. We do this using Docker pull, followed by the ECR URI and the tag name. The second script gracefully stops a running container using Docker stop, followed by the container name. I can also add through just for safety, so the script does not fail if the container does not exist yet. After that, we remove the stopped container from the system. Next, I define a bash variable called secrets.json. This variable stores the output of an AWS CLI command. In this case, the output is JSON string that contains our secrets from AWS Secrets Manager. Then I call AWS Secrets Manager get secret value. This command fetches the actual secret value stored in AWS Secrets Manager. It takes three important arguments. First, secret ID that has value NestJS prod secrets, which is the name of the secret stored in AWS Secrets Manager. As you can see, we first need to create this secret. So let's go to AWS Secrets Manager. Click Store or New Secret. Select other type of secret. Then add all your environment variables. After that, click Next. In the secret name field, enter exactly the same name used in the CI/CD pipeline, NestJS prod secrets. Add a description if you want, and optionally add tags. Leave the rest as default and click Create. Now go back to the CI/CD pipeline and use this secret name. We query secret string to return the secret content itself. And we output it as plain text instead of JSON. After retrieving all the secrets and storing them in the secrets JSON variable, we extract each secret and set it as an environment variable for the application. The final step is to run the Docker container with all environment variables. We use Docker run to create and run a new container, and -d to run it in detached mode in the background. Then we map the host port to the container port. Set the container name. Pass all environment variables. And finally, specify the ECR repository URI with the tag name. At this point, we've finished the pipeline. What happens now is we build the Docker image, tag the image, push it to ECR, pull it on EC2, and deploy the application. All of this is done only using the AWS CLI. That means we are deploying the application manually, step by step. First, we need to install the AWS CLI. Before installing, I check if it is already installed. If you don't see any version, search for AWS CLI on Google and install it based on your operating system. If you are using Windows, download the installer and run it. Next, we log Docker into AWS ECR so we can push and pull images. We ask AWS for a temporary authentication token using AWS ECR get login password. Then we authenticate Docker to AWS ECR. Once authentication succeeds, we can tag the local Docker image with the ECR repository name. After that, we push the image to AWS ECR. Once the push is complete, let's verify it. Go to your ECR repository. You'll see unknown image with the tag latest. If you click on it, you'll see details like image size, status, and digest. Now go back to the code editor. Since the image is pushed to ECR, the next step is to pull it on the EC2 instance and run it. To do that, we need to SSH into our EC2 server. We use SSH-E-I followed by the private key we created earlier, the Amazon Linux username EC2 user, and the public DNS or IP address of the EC2 instance. Then press enter. The first time you SSH into a server, you will see an ECDSA key fingerprint. No worries, this is just a unique identifier for the server. Type yes and continue. Now we are connected to our EC2 virtual machine. Think of this server like a brand new laptop. Nothing is installed yet, so we need to configure everything. First, let's check if Docker is already installed by running docker -- version. If it is not installed, we install it using sudo yum install y docker. This installs Docker using yum with root privileges. After installation, we start the Docker service using systemctl. And enable it to start automatically on system boot. This way, we don't need to start Docker manually every time. Next, we allow the EC2 user to run Docker without sudo. After that, we check the Docker service status to make sure it is running. You can see details like service, state, and memory usage. Next, press Q to exit. Then we check the Docker version again. We also verify that the AWS CLI is installed. Perfect. If you are using another Linux distribution like Ubuntu, you may need to install the AWS CLI manually. At this point, everything is installed and ready. Now we can log in to ECR from the EC2 instance and authenticate Docker using the AWS CLI. We are getting an error unable to locate credentials. This happens because the AWS CLI needs credentials to know who you are and what you are allowed to do. To authenticate with AWS, there are two main approaches. The first method is attaching an IAM role to your EC2 instance. The second method is providing AWS API keys, which include an access key ID or secret access key in your AWS region. However, this second method is not recommended in production because storing credentials manually is insecure. So in this project, we'll use the first and recommended approach, attach an IAM role to our EC2 instance. Now go to the AWS EC2 dashboard, then open the IAM roles page. You can search for an existing EC2 role if one already exists and reuse it. Or you can simply create a new role, which is what we'll do. Here, select AWS Service as the trusted entity type. For the use case, choose EC2 then continue. Next, we need to add permissions. These permissions define what this EC2 instance is allowed to do when using the AWS CLI. First, we add Amazon EC2 container registry read only because we want access to Docker images stored in Amazon ECR. Next, we add AWS Secrets Manager read-only access, so the instance can read secrets from AWS Secrets Manager. Then we add CloudWatch logs full access, which allows full access to CloudWatch logs for monitoring and debugging. Once that is done, click Next. Now give the role a name. You can also add tags if you want. Then click Create Role. Great, the IAM role is now created. Next, we need to attach this role to our EC2 instance. Go back to EC2 instances, select your instance, and under the security section, you'll see that no IAM role is attached yet. Click Modify IAM role. Select the role we just created and hit Update. Perfect. Now, let's go back to our code editor and try again. And this time, it works. We are now authenticated and our EC2 instance can successfully connect to Amazon ECR. That means we can pull Docker images from the ECR repository onto our EC2 virtual machine. However, we now get another error, permission denied. This is a Linux permission issue, not an AWS one. To fix it, run the command nu grp docker. Then retry the command. Once the image is downloaded, we can run it using docker run. This command generates a container ID. Every Docker container has a unique ID. Great, everything now works manually. Now let's move on and deploy our CI/CD pipeline. First, we push our code to GitHub. Then we go to GitHub Actions and the pipeline starts automatically. The CI passes. And the CD passes as well. But when we open the app in the browser, we see an empty page. Why? Because we have not configured the security group to allow traffic to the port opened by our container. To fix this, go back to your EC2 instance, select it, scroll down to inbound roles. You'll see several roles already, but one is missing. Click on the security group link. Then click Edit Inbound Roles. Add a new role with type custom TCP. Port range 3000 and source anywhere. We will also add another rule for port 3001, just in case. Save the rules. Now reload the page, and there is it. Our NestJS API app is running. If we go to /API/v1, we see the main API. And for the API documentation, we visit /API/docs. But we are not done yet. We still need to make a few improvements, like updating the Swagger development server and adding a production server configuration. Instead of hard coding port 3000, it should match the value defined in our environment variables. Next, we need to set up DNS. So what is DNS? A DNS is simply a domain name that points to an IP address. Here is the problem. When you have a front-end application and backend deployed separately, the frontend needs a base API URL to communicate with the backend. You might say, don't we already have an IP address for the backend? Yes, but the DNS provided by AWS is not secure. What does that mean? When you copy an endpoint directly from the AWS console, it is mainly for convenience. It works inside the same VPC, but the traffic is not encrypted by default. So if you try to use that endpoint from the front end, you will likely get security errors. So what is the solution? First, buy a domain. Second, create a DNS record. Third, point that DNS record to your backend's public IP address. And that is exactly what we are going to do. I already own a domain on Vercel called goaltracker.live. So I create a subdomain for the backend. In my DNS dashboard, I add a new record. The name is YouTube Nest API. Type is A. Value the public IP address of the NestJS API. And TTL is 60. Once that is done, we need to configure our EC2 virtual machine. We connect again. And update all installed packages using sudo yum update. So, what is Nginx? Nginx is a web server and a reverse proxy. As a reverse proxy, it listens on ports 80 and 443 and forwards incoming requests to our application. We install it then starts and enable it using systemctl, so it automatically runs when the machine boots. Finally, we install certbot. Certbot is a tool that automatically issues and renews SSL TLS certificates, allowing our application to run securely over HTTPS. Now, I'm going to stop Nginx for a moment. The reason is that we are about to run certbot to encrypt our domain and generate an SSL TLS certificate. Certbot temporarily starts a stolen web server to perform domain validation for the domain name we want to secure. One important thing I forgot earlier is to use the cert only option. We only want to obtain the SSL TLS certificate, nothing else. During this process, you will be asked to provide your email address, accept the terms of service, agree to receive notifications before certificate expiration. Once the first certificate is issued, your request is saved and certbot will automatically renew the certificate in the background. But we are not done yet. Now we need to configure Nginx. First, open the Nginx configuration file. Inside this file, we are going to define two server blocks. The first server block listings on HTTP port 80 from youtube.goldtracker.live. Its only job is to redirect all traffic permanently to HTTPS. The second server block listings on HTTPX port 443 for the same domain. This one tells Nginx to use the SSL TLS certificate and private key that certbot generated. Once this is done, save the file and exit. To make sure everything is correct, we test the configuration using sudo nginx t. Oops, the test failed. Let's open the file again and check the error. I forgot the letter O in one of the directives. Let's fix that. Save the file and test again. Perfect. The configuration is valid. Now we restart Nginx. Next, open the domain in the browser. Good job, it works. Let's check the main API route. And also the Swagger API documentation. Amazing. And now we also have an SSL certificate, which means our connection is fully secure. This allows us to safely use this base URL as a public API endpoint in our front-end application. Now we are going to add this URL as a production server. So go to main.ts, add a new server configuration. Then push the code to GitHub so the application redeploys. Great, the pipeline runs successfully. Let's reload the NestJS API again. As you can see, we now have both development and production servers. The dev server is for local testing. The production server is for live usage. For example, if I select the dev server and try to call the main API route. It fails. But when I switch to the production server, everything works perfectly. We can also test other endpoints like product. Now let's talk about monitoring. AWS CloudWatch is a monitoring and observability service from Amazon Web Services. It collects logs, metrics, and events, helps monitor performance, detects issues, and supports troubleshooting in production. When we deploy on NestJS API or EC2, we want to know what's happening every second. In development, we use the terminal. For that, in production, CloudWatch handles logs and live metrics. The first thing we need to do is pass extra logging options when running our Docker container on EC2. So open the CI/CD pipeline. Here, we add log driver, AWS logs. This tells Docker to send all container logs to CloudWatch logs. Then we add log OPT to specify AWS region, log group name, and log stream name. Once that is done, go to AWS dashboard and search for CloudWatch. Under log groups, click Create Log Group. Use the same log group name you defined in the CI/CD pipeline. Set the retention period to 1 month, which means CloudWatch will automatically delete logs after 30 days. Create the log group, then open it. CloudWatch will automatically create log streams. To trigger this, we deploy the application again. Once the deployment finishes, a new log stream appears. When we open it, we can see default NestJS log, database logs, application runtime information. Great job! Monitoring is now fully set up. Finally, if you don't want to be charged, you should clean everything up. First, go to Amazon EC2 delete all Docker images. Then delete the repository itself. Next, go to EC2 instances and select your instance. If you only stop the instance, the application won't run anymore, but you may still be charged because the virtual machine still exists. To avoid all charges, you must delete the instance completely. Do the same for secrets manager keys, CloudWatch log groups. You can keep your IAM users and configurations if you plan to reuse them later. And that's it. This is the final part of the DevSecOps Cloud Security course, and also the last part of the Full Stack E-commerce course. I hope this helped you understand what it really means to be a full stack developer in the real world. The goal was to prepare you for reality by teaching front-end development, back-end development, DevOps, and cloud engineering, all in one path. Next, you can go even further by learning AI system development. And that is exactly what's coming next. In the next project, you'll learn how to build a full-stack AI SaaS agent, something you have probably never seen on YouTube. This project will help you master the most in-demand AI frameworks such as LangChain, LangGraph, Gemini LLM, AI APIs. You'll learn how to build RAG systems, how to design optimized RAG pipelines, how to work with production-grade AI architectures. This is not a toy project. It's a real project that can help you get hired as a full-stack AI engineer. The project will be available on my Patreon channel. See you there.